Hello, my precious friends. I really hope that you are doing great. Welcome to our today's class. It is our first lesson on the 10th and last topic of Form 3 work, which is called gas laws. As usual, let me comment by giving the quote of the day, which states that well done is far much better than well said. We shall discuss that quote at the end of our class today. So under gas laws, we'll basically be looking at the three gas laws, that is the Boyle's law, the Charles law, and the pressure law. Then after that, we shall look at the combined gas equation. Then finally, we'll simply look at the kinetic theory explanation of the three gas laws. So for today, we are discussing what we call the Charles law. Let's start by understanding the origin of the term Boyle's law. So the term Boyle's law originated from the name of a philosopher, a physicist, a chemist, and an inventor called Robert Boyles, who was actually born in Ireland. So he was the first person to experimentally study the relationship between pressure and volume of a fixed mass of a gas, that is, whenever temperature is kept constant. So under Boyle's law, so a gas, usually air, is trapped in a glass tube by light oil. So this is our light oil, then this is what we are calling our glass tube. Then pressure is exerted on the oil by a pump. So this is the connection to the pump, which compresses the gas. So pressure is measured with a pressure gauge. So the purpose of the pressure gauge is simply to measure the pressure, and of course the volume is measured by the length of the air column. Now it is important to note that in this particular glass tube, we usually use we use a glass tube of a uniform cross-sectional area. For example, we are using a cross-sectional area of 1. We know that volume is equals to cross-sectional area multiplied by height. So whenever you keep the cross-sectional area constant, it simply means that the volume will always behave directly proportional to the height, such that if the volume is supposed to increase, the height will also increase. If the volume reduces, the height of the air column is also going to reduce. So suppose that the cross-sectional area of our glass tube is actually 1. So it means the volume will always be equal to the h, because when you multiply any value of h times 1, you'll just get that particular value of h. So we are using a uniform cross-sectional area such that the height is able to give us the volume of the air column. So a set of readings are usually taken and tabulated. Then the graphical representation of the results is as shown below. So you simply vary this particular pressure. Of course, when you apply more pressure through this particular arm, we expect this particular oil to move upwards and exert pressure on the air. That is air that is trapped within this particular column. Of course, when you exert pressure on the air, we expect the air to be compressed and therefore reducing in volume. Therefore, whenever you increase pressure, the volume will always going to reduce. That is the volume of the air column. Hence, the height of the air column will also be shorter. So actually pressure, the more the pressure, the lesser the height of the air column, hence the lesser the volume. And of course, the lesser the pressure, the more the height of the air column, and of course, the more the volume of air. Because when pressure is less, it simply means that the oil will actually move upwards, creating more space on this side. Therefore, the air will expand, hence increasing the volume, and therefore increasing the height of that particular air column. Now consider these sample values that were collected from a similar experiment. So when the pressure through this particular column recorded by the pressure gauge, when the pressure was 10, the volume was observed to be 3. When the pressure was 20, the height of the air column was 1.5. When the pressure was 30, the height of the air column was also observed to be 1. So notice that the pressure increases from the smaller value, then it is increasing up to 30. At the same time, the volume is now reducing. So this is actually an inverse proportionality. So if we sketch a graph of pressure against volume, so this will be our graph. So when pressure is 10, the volume is 3. So when the volume is 3, the pressure is actually 10. So you simply plot here. Then when the pressure is 20, the volume is 1.5. So when the pressure is 20, the volume is 1.5, hence this star here. Then when the pressure is 30, the volume is 1. So you can see 30 is corresponding with a volume of 1. So when you sketch that graph, this will be the graph obtained. So this one simply shows that pressure and volume are inversely proportional to one another, such that when pressure is maximum, the volume is minimum, but when the pressure is minimum, the volume actually becomes maximum. So this is the graph for pressure against volume. Then we also want to see the graph of pressure against the reciprocal of volume, or the reciprocal of the air column. So to find the reciprocal of the air column, we simply introduce another column of 1 divided by V. So we'll simply be taking the values of, for example, if you take 1 divided by 3, you'll obtain 0.33 recurring. Then if you take 1 divided by 1.5, you'll simply obtain 0.66 recurring. Then if you take 1 divided by a volume of 1, you'll simply obtain 1.00. So these are the values for the reciprocal of volume. So you simply take 1 divided by the values of the volume, hence you fill this particular row. So from there, we can now easily plot a graph of pressure against the reciprocal of volume. So when the pressure is 10, the reciprocal of volume is actually 0.33. So you can see pressure is increasing from 10 to 20 to 30. Then the reciprocal of volume is also increasing from 0.3 to 0.6 to 1. So now this is a direct proportionality, such that when one quantity increases, the reciprocal, when pressure increases, the reciprocal of volume also increases. So this is a direct proportionality relationship. So when the pressure is 10, the reciprocal of volume is 0.3. So 10 corresponds with 0.3, hence this star here. Then when the pressure is 20, reciprocal of volume is 0.7. So I've just rounded off. So 20 corresponds with 0.7, hence this star here. Then when the pressure is 30, the reciprocal of volume is actually 1. So 30 corresponds with 1. So when you plot the graph, you'll obtain a straight line graph. So this one simply shows you the direct proportionality relationship of pressure and the reciprocal of the volume. Then we also need to plot a graph of PV against pressure. So the graph of the product of pressure and volume against pressure. So to obtain values for pressure times volume, I'll simply be taking the value of P, I multiply by the value of volume. So for example, if you take 10 multiplied by 3.0, you'll actually obtain a PV of 30. If you take 20 multiplied by the value of V, so 20 times 1.5, you'll get 30. 30 times 1, you simply obtain 30. So you can see that the value of pressure, the product of pressure and volume, is actually remaining constant. So it is 30, 30, 30. So it is constant. So if you plot a graph of PV against pressure, for example, 30 corresponds with a pressure of 10. So 30 corresponds with a pressure of 10. Then 20 corresponds with 30. So when the value of pressure is 20, PV is still 30. Hence this mark here. When the pressure is 30, the PV is also 30. So if you plot the graph, you'll obtain a straight line graph showing that PV actually remains constant regardless of either an increase or a reduction in the pressure of the gas. So you can be asked to sketch any of these graphs. So you need to think in that line and of course have the graphs. Therefore, from the first graph of pressure and volume, we can see that when pressure is maximum, the volume is minimum, but when the pressure is minimum, the volume becomes maximum. So they are inversely proportional to one another. Therefore, the Boyle's law states that, so from this graph, the Boyle's law states that the pressure of a fixed mass of a gas is inversely proportional to its volume, provided that temperature is kept constant. So when you keep the temperature constant, the pressure will always be inversely proportional to volume, such that whenever you have maximum pressure, the volume will always be minimum, but whenever you have minimum pressure, the volume will always be maximum. So mathematically, let's represent pressure is represented by P, then of course volume is represented by V. So because they are inversely proportional to one another, so this is our proportionality simple. So mathematically, the Boyle's law can be summarized as pressure is inversely proportional to the volume. It is inversely proportional to the volume. So of course, to remove the proportionality simple, we simply introduce equal sign with a constant, and our constant in this case is K. Therefore, P will be equal to K multiplied by 1 over V. So we want to make K subject of the formula, so I'll simply multiply both sides by V. So of course, V and V will cancel in this side, then P times V, I'll simply obtain PV. So this will become, if I multiply both sides by V, I'll have PV being equal to K, of course, where K is the constant. So if PV is equals to a constant, it simply means that if you take the product of pressure and volume at any given point, we expect that particular value to be constant, just the way we saw in this particular that is in our table here. So regardless of the variation in pressure, the product of pressure and volume will always be a constant value. For example, here we are having a constant value of 30. So for example, if we are talking of this case, the value of K, or the constant, will simply be 30. So if you take the product of pressure and volume at any given point, you expect a constant value. Therefore, the pressure at point 1 multiplied by the volume at point 1 must be equal to pressure at point 2 multiplied by the volume at point 2. Next. Our first example reads that the figure below shows a horizontal tube containing air trapped by a mercury thread of length 24 centimeter. Then the length of the enclosed air column is 15 centimeter and the atmospheric pressure is 76 centimeters of mercury. Under pressure lesson 1, we gave various units that can be used to measure pressure. We talked of atmospheres, we talked of pascals, we talked of Newton per meter squared, we also talked of millimeters of mercury. So the other unit that can be used to measure pressure is centimeters of mercury. Remember from chemistry, Hg is a symbol that stands for mercury. Therefore, 76 centimeters Hg simply means 76 centimeters of mercury, which is simply the pressure strictly due to the mercury column. So Roman 1, we are told to state the pressure of the enclosed air. So it is important to note that when the tube is lying horizontally, actually this particular air, that is the air column, it does not experience any pressure due to the mercury. So the reason being, remember, the pressure due to the mercury is usually the pressure due to the weight of that particular mercury. And we know that because weight is equals to mg, the weight depends on gravity. And we know that gravity will always act vertically, or it will always pull objects toward the center of the earth. Therefore, the pressure due to the mercury is actually due to its weight, and it is acting downwards. But our air, that is the tube, is lying horizontally. Therefore, this particular air will not experience any pressure due to the mercury when the tube is lying horizontally. So the reason we have said is because the pressure due to the weight of the mercury will actually act downwards or vertically. Therefore, the only pressure, so provided that this particular mercury is still in this particular horizontal tube and it is not getting poured out, it simply means that the pressure acting from the right hand side is equals to the pressure due to the air that is trapped within that particular tube. So that simply tells you that the pressure due to the air will be equal to the pressure acting from outside. Then we know that the pressure that acts from outside is usually the atmospheric pressure, or the pressure due to the air column, which is outside that particular tube. Therefore, in short, the pressure due to the air will simply be equal to atmospheric pressure. So remember, the pressure due to the mercury will not exert, that is, the mercury will not exert any pressure on this particular air. The reason being, the pressure due to the mercury is the pressure due to the weight of that particular mercury, and weight acts vertically and our tube is lying horizontally. Therefore, no mercury will exert pressure on this particular air when the tube is lying horizontally. However, mercury can only exert pressure on the air when the tube is lying vertically, because that will be in the same direction with the gravity. Therefore, the pressure due to the air is equals to atmospheric pressure, and the atmospheric pressure we are given as 76 centimeters of mercury. Therefore, pressure due to air is equals to pressure due to that is the atmospheric pressure, which is equals to 76 centimeters of mercury. Then in part B, we are told that the tube is now held in a vertical position with the open end facing upwards as shown in the figure below. So part A, determine the pressure of the enclosed air. Now remember, when now the tube is laid vertically, it means now the mercury will actually exert pressure on this particular air, because the pressure due to mercury is usually the pressure due to the weight of the mercury. And we know that because weight depends on gravity and gravity acts downwards, it means that when the tube is vertical, this particular mercury will exert pressure on this particular air. Therefore, the total pressure being exerted on this particular air will be the pressure due to the weight of the mercury plus the atmospheric pressure, which is acting from the upper end or from the opening. Therefore, the total pressure acting on the enclosed air, P air, will simply be equal to the atmospheric pressure plus the pressure due to the mercury column. So this particular mercury column plus the PA. Therefore, pressure due to air is equals to atmospheric pressure. We were given as 76 centimeters of mercury. Remember, atmospheric pressure is usually a constant, plus pressure due to the mercury column. So we are given the column of the mercury as 24 centimeters. Therefore, the pressure due to this mercury column will simply be 24 centimeters of mercury, because it is the column of mercury. Therefore, the pressure due to the mercury column is equals to 24 centimeters of mercury. So if you take 76 centimeters of mercury plus 24 centimeters of mercury, you simply obtain pressure of the enclosed air being 100 centimeters of mercury. Then Roman 2, they want us to find the length L of the enclosed air column. So they want us to find the length of the enclosed air column. So at this point, we'll simply introduce the Boyle's law, which gives us the relationship between pressure and volume. So if we take the pressure and volume in the first case, it must be equal to the product of pressure and volume in the second case. That is courtesy of the Boyle's law, which stated that, which told us that the product of pressure and volume should be constant at all points. Therefore, the pressure P1, so the pressure in the first case of the air, it was actually 76 centimeters of mercury. So P1 is 76 centimeters of mercury multiplied by the volume in the first case, so the volume of the air column. So remember, we also said that volume will just behave the same way with the length of the air column, because remember, volume, that is, volume is equal to cross-sectional area times height. So if we take cross-sectional area to be a constant of 1, so it simply means that the volume in that case will be equal to the height, because volume and height are usually directly proportional to each other. Therefore, our volume V1 will just be equal to the length of the air column in the first case, which was 15 centimeters, then is equals to P2, so pressure in the second case. So the pressure of the air in the second case was 100 centimeters of mercury. So P2 is 100 centimeters of mercury multiplied by the volume of the air column in the second case. So remember, volume of the air column, similarly, volume of the air column will simply be equal to the height of the air column in the second case, which is actually L. So the volume V2, so let's just use the term V2. So if I make V2 subject of the formula, I'll simply divide both sides by 100 centimeters of mercury. Therefore, V2 will be equal to 76 centimeters of mercury times 15 centimeters divided by 100 centimeters of mercury. Therefore, V2, which is simply equal to the length of the air column in the second case, which is L, will give us 11.4 centimeters. So that is the volume V2 of, or simply the length of the air column in the second case. Next, our second example reads that a column of air 26 centimeters long is stopped by mercury thread 5 centimeters long as shown below. When the tube is inverted, the air column becomes 30 centimeters. What is the value of the atmospheric pressure? So we simply use the Boyle's law. We compare P1 V1. We also compare it with P2 V2. So in our first tube, V1, or the volume of the air column, will simply be equal to the length of the air column, which is equals to 26 centimeters. Therefore, V1 is equals to the volume of the air column in the first tube, which is given as 26 centimeters. Then P1, so the total pressure exerted on the air in this particular column, will be equal to the pressure due to the weight of the mercury plus the atmospheric pressure. We said that when the tube is vertical, because the weight acts downwards, it simply means that the weight, that is the weight of the mercury, will actually exert pressure on this particular air. Therefore, the total pressure being exerted on our air is simply atmospheric pressure PA plus the pressure due to the mercury, that is PHG. Therefore, P1 is equals to atmospheric pressure plus the pressure due to the mercury column in the first tube. So of course, the PA is unknown, or the atmospheric pressure is the unknown. So atmospheric pressure, which is PA plus 5 centimeters of mercury. So that will be our total P1, or the total pressure being exerted on the air in the first column. Then we move to the volume of air in the second column is equals to the length of the air column in the second tube, which is given as 30 centimeters. Therefore, V2 is equals to volume of the air column in the second tube, which is given as 30 centimeters. then P2 will be given by, so the total pressure being exerted on this particular air will be the difference between atmospheric pressure and the pressure, the weight of the mercury column. But we need to subtract the weight of the pressure due to the weight of the mercury column from the atmospheric pressure. The reason being, provided that this particular mercury is still within this particular tube, it simply means that atmospheric pressure is still greater than the pressure due to the weight of this mercury column. So that is why I'm taking PA, atmospheric pressure, minus the pressure due to the mercury column, and not the vice versa. However, if the pressure due to the weight of the mercury column, if it was greater than atmospheric pressure, this actually mercury will have flowed outside the tube. But provided the mercury is still within the tube, it means the pressure being exerted on the air will simply be equal to the difference between atmospheric pressure and the pressure due to the mercury column. So again, because they are moving in opposite directions, we know that when the tube is inverted, now the atmospheric pressure will act from the opening, which is downward. Therefore, the atmospheric pressure will act upward, while the weight, because the pressure due to the mercury depends on the weight of that particular mercury, and we know that the weight will always act downwards because it depends on gravity, which always pulls object downwards. It simply means that you can see the direction of the pressure due to the mercury is reversing the direction of atmospheric pressure. Therefore, pressure on the air column will be PA minus Hg, because they are moving in opposite direction. That's why we are subtracting. For this case, we were adding because atmospheric pressure and the pressure due to the weight of the mercury were acting in the same direction. So in this case, I'll take PA minus pressure due to the mercury as my P2. Therefore, P2 is equals to the pressure due to atmosphere, or the atmospheric pressure, minus the pressure due to the mercury column in the second tube. Again, we have said we are subtracting because of the change in direction. So the weight is acting downwards while the pressure is acting upward. Then we are taking PA minus pressure due to the mercury, because atmospheric pressure will always be greater than the weight of the mercury. That is why the mercury is still within that particular tube. Therefore, P2 is equals to atmospheric pressure minus the pressure due to the mercury, which is actually 5 centimeters of mercury, because the length of the mercury column is 5 centimeters. Therefore, the pressure due to the mercury will be 5 centimeters of mercury. Then Boyle's law required that P1 V1 must be equal to P2 V2. So P1 is actually PA plus 5 centimeters of mercury. So PA plus 5 multiplied by V1, we already have it as 26 centimeters, is equals to P2 is PA minus 5 centimeters of mercury. So PA minus 5 multiplied by V2. V2, we have it as 30 centimeters. So if I open this particular bracket, I'll simply have 26 being multiplied by PA. So I'll get 26 times PA, then 5 times 26. So 5 times 26 is equals to PA multiplied by 30. I'll have 30 times PA. Then negative 5 multiplied by 30. I'll just have negative 5 times 30. Of course, 26 times PA, I'll just get 26 PA, where PA is the atmospheric pressure. Then 5 times 26, I'll get 130. Then 30 times PA, I'll just get 30 PA. Negative 5 times 30, I'll get negative 150. From there, I want to collect the like terms, so I'll take negative 150 towards the right hand side, so it will become a positive. Then I take 26 PA towards the left hand side, hence it becomes a negative. Therefore, 150 plus 130, I'll simply get 280. Then 30 PA minus 26 PA, I'll simply get 4 PA. Therefore, if I divide both sides by 4, I'll simply get PA being equal to 280 divided by 4. Therefore, the atmospheric pressure was equal to 70 centimeters of mercury. Again, centimeters of mercury, because we were using mercury in this particular case. Lastly, I have an exercise that I recommend you should try at your own free time to gauge the understanding of the examples that you have just done. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in. And as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that, "Well done is far much better than well said." The quote is reminding us that actions will always be better than words, because actions can get you results, but words will never give you results. Therefore, we should strive to execute stuff instead of just planning and procrastinating our actions. And lastly, recall that unless you try and fail, you will never learn how to do it better next time. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you're new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. If you know anyone that you wanted to think could benefit from this content, kindly refer them to Kind Tuition Academy or just share my link to them. Until next time, this is Kind Tuition Academy. Thank you very much.